Good morning. Let's try not to step on cables here. Yeah, let's get started. This morning will be all about hot swapping stuff, and in particular hot swapping container platforms. But before we get into container platforms in general, let's briefly look at the evolution of hot swapping. Hot swapping has been a big part of how we prevent, how we handle, how we recover from failure for years, but it has certainly evolved over time. 20 years ago, we mostly had private data centers. We had physical servers in them that ran specific applications, and the application was tied to the specific server. So if availability of your application was of absolute critical importance, you had to invest a lot of money in, well, very expensive hardware where you could hot swap, like from disks to CPUs to memory, RAID cards, whatever. As you can imagine, IBM made a lot of money back then. And then in the early 2000s, virtualization happened. Technology existed before, but it was finally mature enough to use at a large scale, and it offered some pretty great benefits. You could use your compute resources much more efficiently. So instead of 15% utilization, you could actually overcommit, finally. But also you could move your VMs around. So instead of investing heavily in very expensive hardware, you could get, well, pretty much commodity hardware and basically swap your hypervisor. With applications no longer tied directly to a physical server, so you could actually save money without compromising on the application availability. And then we moved to the cloud. We got tired of running our own data centers, and it seemed like a pretty good idea to simply put our stuffs in someone else's data center, like Amazon's, for instance. But as it turned out, well, it wasn't just a case of taking whatever we had and copying it onto someone else's data center. Moving to someone else's data center meant we had to surrender control over the physical hardware. We had to give up something like live migration. So our applications were once again tied to a physical server, but this time we had no control over the server. We didn't even know what kind of server it was, where it was, if it was running, what kind of RAID card it had, if it even had any form of redundancy. So we needed hot swapping in a different way, but you can't really hot swap your cloud. So pretty much in parallel of that, there were some other interesting developments in the data center realm, like container technology and a focus on more dynamic infrastructure. With Docker, we can create applications that are no longer tied to a specific operating system. We can create applications that are no longer tied to a server, because the application is unaware of the underlying operating system and vice versa. We have advanced schedulers, we have service discovery mechanisms, and we have loads of software-defined something solutions. So maybe we can achieve the hot swapping that we need in our container platform. But there's a lot of moving parts there. So this is not necessarily going to be easy, but I think it's what we need to do. Because basically, if we want to hot swap stuff, we need a container platform where we not just can hot swap something, but we need to be able to hot swap every component automatically. Because if we can make that happen, well, basically we can sleep at night, because we end up with a platform that can repair itself when something breaks. So instead of getting paged at 3 a.m. because you have to fix a cluster, well, maybe you're getting an email in the morning about what the platform did last night, a bit like this. But it gets better. If we can hot swap every component of the platform at any time, we can do maintenance at any time. So instead of doing maintenance in a scheduled window on a Saturday night, you can basically hot swap right now. And that's what we're getting for free. Well, before I get into how you can actually do that, let me introduce the reference stack for today. This is a real-world stack that's running at one of our clients. It's a large international company, and I will use it to explain some of the principles that I will explain later on. So it's pretty readable, I think. If some of the technology is unknown to you, don't worry. We'll get to that later. So how do you actually build a hot-swappable container platform? Well, the implementation specifics heavily depend on your technology choices. For instance, our reference stack uses CoreOS and Fleet. It will definitely be different than Kubernetes, for instance. But that's not what I want to focus on today. Instead, I want to focus on 6 general principles that you can apply to whatever technology choice you make to build your own hot-swappable container platform. And I will give them away immediately, and then dive in. The first is infrastructure as code, or as I like to call it, if it isn't code, it doesn't exist. By defining your infrastructure as code, you will end up with repeatable, testable infrastructure, predictable changes, and with much less documentation. Because you have code documenting your entire infrastructure. It documents the dependencies within your infrastructure, the configuration, the relationships. If you have that, your regular documentation can be focused on overall architecture. So instead of documenting everything you have, you simply document everything on a more global level and document how it works. In my experience, you end up with a lot less documentation, more useful documentation, and documentation that doesn't lag behind. There are a lot of solutions available if you want to codify your infrastructure. And depending on what you're building, how you're building it, any of them can be the right choice. But for a reference stack, we use Terraform. If you're not familiar with Terraform, Terraform gives you a declarative language to describe your infrastructural assets across providers. It describes their configuration, it describes their relationships, and because Terraform can run across providers, you can, for instance, define a Cloudflare DNS record that takes the IP address of an AWS instance as its value. And by simply defining that, Terraform will understand there's a relationship and understand the order in which the resources need to be created across providers. So that's pretty neat. From a workflow perspective, Terraform's pretty straightforward. You write code in your favorite editor, you apply version control, obviously. Then you can see what Terraform is about to do using Terraform Plan. You can apply your changes, running Terraform apply, and you can do something, well, that's as dangerous as it is easily. You can destroy everything by running Terraform destroy. So this might be dangerous on one hand, but it also means you can clean up after yourself, and you can do it easy. So it's very useful if you're working with disposable environments. For instance, when your entire infrastructure is codified, like a reference platform, you can create multiple instances from it. So you can create a production platform, you can create a non-production platform, and you can create an ad hoc instance of the platform to simply, for instance, test an upgrade of Consul on a real-life platform that's completely isolated from everything else, but it's identical. To give you a sense of how easy this is and how short this takes, we can spin up a small-scale but full-featured version of the reference stack in under 10 minutes. So that's a completely hot-swappable container platform, full-featured, including service discovery, routing, databases, etc., under 10 minutes. If we look at the entire production platform at this client, that takes under 30 minutes from 0 to completely up and running. So Terraform can do all kinds of awesome things. It's fast, it's flexible, but that flexibility can also be a downfall sometimes. For instance, Terraform offers provisioners that you can use to provision an instance after you created it, for instance. You can run remote commands over SSH, you can run shell scripts, chef cookbooks or Ansible playbooks, anything you like. I would recommend avoiding these provisioners. It makes your Terraform run much slower, it's less dependable, and if, for instance, your SSH connection fails, your Terraform run fails. So if you really need to install and configure 200 packages on your newly created instance, well, maybe you should look into something different, like Packer. You just had to talk about that. And create your provisioned image at that point. Deploy those directly, because deploying a pre-provisioned image will be fast, will be dependable, will be reliable, and also will take way less time. And as a bonus, you can actually test the outcome of your provisioning steps at build time. The second principle I want to talk about is a static host OS. This is basically moving on from the previous slide. It means having a host OS that requires minimal, or rather no, provisioning on runtime or runtime configuration. You can create a static host OS by pre-provisioning when you build an image. But what's even better than pre-provisioning a pretty fat OS is create a minimal host OS, like CoreOS, for instance. because everything, including system services like monitoring or logging agents, are running in a container. The host OS is actually very, very tiny. It simply needs to be able to run containers and participate in a cluster. And everything else is a building block that you can add later. And by having a static, minimal host OS, your OS becomes a building block by itself. It has a few advantages. First of all, creating an instance from a pre-provisioned image will be much faster than doing all kinds of provisioning at boot, as I mentioned. And secondly, it's likely to be more secure. If you're using pre-provisioned images, you can run all kinds of tests during build, basically as Werner described in his previous talk, to see if your instance still passes all kinds of security and compliancy checks. When you run provisioning at boot, there's actually not even a guarantee that you end up with what you wanted. Also, if you're using a minimal dedicated OS like CoreOS, there are very little moving parts, so you have a very small attack surface. And finally, you will save time on debugging stuff, because there will be no boot time issues that are related to provisioning, because you're not doing any. And if you're using CoreOS, there's even more time saving. Because if you're using CoreOS, you don't have to maintain your image. There are ready-to-use CoreOS images that you can basically just use, and they do all you need. The third principle is to externalize data. If we want to treat our host OS and the instances we create based on that as basically Lego bricks, we shouldn't use our host OS to store any important data, right? Because instances can fail, or actually we want to take them down as part of our maintenance. So basically, we shouldn't store anything locally unless it's OK if we lose it. Like a local cache, for instance, that's perfectly fine to store locally. We can just lose it if an instance dies. If your data is part of a clustered service where it's replicated across multiple nodes, again, no problem storing it locally because it's replicated. But if you don't want to run your own clustered storage service or anything, you should either look at your cloud provider's offerings for a dedicated storage backend or a database that has built-in fault tolerance depending on the kind of storage that you need. But for a reference stack, we use Amazon's S3 as a backend for file-based storage, and we use Amazon's RDS, or for those who aren't familiar with that, it's basically database as a service. For relational databases, because those databases are high available. They are in multiple availability zones within a region. They can be encrypted. They're automatically backupped. It's pretty awesome. So those were the first three principles. And they were mostly about predictability, about repeatability, about doing things neatly. The next ones will be mostly about failure. Let's start by handling failure, because if we want to get anywhere close to hot swapping anything, we need to make sure we can handle some degree of failure. If you have a server that allows for hot swapping of disks, it doesn't make much sense to simply put in one disk. You will put in at least two. The same goes for components of container platforms. There's a saying, 2 is 1 and 1 is none. Oh, this definitely applies here. Your platform shouldn't have a single point of failure anywhere. So for a reference stack, it means we're running a CoreOS cluster instead of a single host. We're running Consul, which is our service discovery, and Fleet, our scheduler, in a clustered setup. We're running multiple instances of our proxies. We use load balancing in front of them, et cetera, et cetera, et cetera. Basically, we can have n-1 of any component without entering a failed state, and so should you. You should always be able to gracefully degrade. Because if you want to hot swap, you should be able to lose something. Or we can build clusters all we want, and we can deploy 2 or 3 or anything as much as we want, but that only means that the lights stay on. It only means that if something goes wrong, your customers can still reach your website or your application, but you still need to fix something. It still means you're getting paged at 3 a.m. It still means you have to fix stuff. So we're not hot swapping anything yet. So how can we make sure we can actually recover from failure? The first thing is to use autoscaling. If you're using one of the major cloud providers, there will be some sort of autoscaling available. Names might vary, functionality might vary. For a reference stack, we're using AWS, so we'll stick to Amazon terminology here. If you want a hot-swappable platform, we need to consider everything that we have there, groups of cattle. If you're not familiar on what I mean by that, Google pets versus cattle later. But even things like Bastion nodes or NAT instances, they should be cattle. There can be no pets on our platform. And what autoscaling does, it allows us to automatically scale the amount of cattle. But that's not what we're really interested in today. Even if we're not thinking about scaling, we should still use autoscaling. Because what autoscaling will also do for you is automatically replace a failed instance. But that doesn't happen magically. It does mean you have to think about a few things. And the first thing is health checks. Because when is my node actually healthy? Is it healthy when it responds to ping? Is it healthy if some TCP port is reachable? Or do we want a more elaborate HTTP health check endpoint? And what should it exactly do? Is it healthy when, well, I can basically connect to port 80 and do a get slash and, well, there's a web server running. Am I happy then? Or should that health check endpoint return a 404, for instance, when my logging agent isn't running? Or maybe my registrator isn't running, so I can actually start containers, I can run containers, but I can't register them in the service discovery, so I can't use them. So what should this endpoint be doing? The second thing you need to consider is recovery times. Because when something goes down and we spin up a new one automatically, when is it actually healthy? When can I trust the health checks that my autoscaling group does? Will that take 2 minutes or maybe 10? It's important to have a sense of how long does this take. It's also important that this is somewhat predictable. So remember how I mentioned earlier that you should avoid using provisioners? Well, here's why, again. Because using boot-time provisioners to install 20 packages makes recovery times unpredictable. Because at some point it may take 2 minutes, at some other point it may take 15 minutes. So when is your node healthy? Also, it will mean it will take longer. And don't forget that we're recovering from a degraded state, so speed is at the essence here. If you actually want to use an autoscaling group for autoscaling, there's a third thing to consider, which is what metric do I use? When do I want to scale and why? Do I want to scale based on the amount of TCP connections? Or do I want to scale based on the CPU load or maybe memory? The third one is particularly interesting, because if you're going to do this and you're going to scale on memory, be sure to apply some limits to how far you can actually scale. Because you wouldn't be the first or the last to autoscale to like 500 nodes based on an application with a memory leak. So don't do that. So we're codifying everything. We use static host OSs. We're externalizing data, running everything in autoscaling, high available setups. How does this make our platform repair itself? Well, let's look at an example. We have a reference tag. We use CoreOS. What if an instance fails? Well, let's look at the healthy part first. We have an autoscaling group with 4 CoreOS nodes, and each are running a proxy. Some are running an app, some are running a backend server, and we have an elastic load balancer in front of them. So, disaster strikes. We lose a node. What happens at first is that the elastic load balancer will notice that one of the proxies has gone missing, and it will simply stop routing traffic to it. So that's done. The second thing that will happen is the scheduler will kick in, because it just lost 2 application containers. So it will simply reschedule them to other servers. So again, we end up with, well, 3 containers of the app, 3 containers of the backend servers. And then finally, the autoscaling group notices that one of my nodes is missing. It will start a new one. It will automatically join the CoreOS cluster, and it starts running all the services that should be running on each CoreOS node, like the proxy, like the logging agent, like registrator, et cetera, et cetera, et cetera. Now let's see what it means for you. The platform took 5 minutes to fully recover from its degraded state. 5 minutes. And it recovered without any human intervention. So if this happens at 3 a.m., you're not getting paged. You're getting an email in the morning, if you configured it, telling you that, well, I replaced a node and it took 5 minutes. I hope you had a good night's sleep. So let's move to the final key principle. that I want to talk about today. It's called automated repeatable bootstrapping. Now, what is that? Earlier, we mentioned that everything should be highly available, it should be fault tolerant. Well, that's cool, but for many components in our container platform that actually hold state, like for instance, our service discovery, it takes more than just run a few. So what do we need to do here? Well, basically, to make things like schedulers or key value stores, service registries, etc. work, we need a clustering. And if we just cluster things, we're just making sure that the lights stay on, like I mentioned earlier. So we not just need to cluster, we need to cluster in such a way that we can recover regardless of state. So if your autoscaling group launches a replacement node for your failed instance, it should be able to automatically join the existing cluster and replace the failed node. So how do you do that? For an example, I'm going to use etcd. If you're not familiar with etcd, don't worry, because I could have used basically every scheduling or clustered application here. But what etcd does is it's a distributed key value store, and it's an essential part to use Fleet, which is the default scheduler with CoreOS. But like I said, I could have used pretty much anything here. If we look at the official documentation for etcd, there's mention of 4 possible ways to bootstrap. Let's take a look. The first method is to use a public discovery service. You basically request a token from that service, and you include it in the user data for your CoreOS nodes, and you'll end up with a cluster. This is actually the recommended method for bootstrapping etcd. And it takes not a lot of effort on your side. You simply request a token. But you are introducing an external dependency for something that's critical for your scheduler, which is obviously one of the more critical components of your container platform. So not sure if that's a good idea, because what if the discovery service doesn't work? Then you don't end up with a cluster. But it gets even worse. If one of your cluster nodes fails and your autoscaling group creates a new one, it will have a different IP address. And to then rejoin the cluster, you have to do things manually. So, no public discovery for us. What other options do we have? Well, the second option is to run the discovery service ourselves. This removes the external dependency, but we end up with all the other problems we already had. Plus that now we have to run a service, and we don't know where to run it because we are still bootstrapping our platform. So we have a chicken-egg problem instead. The third option is to use a DNS record. There's no external dependency, there's no infrastructure that we need to run ourselves, because basically most cloud providers provide some form of DNS. But we still need to manually fix stuff, because no one will update the DNS record automatically. And even if it did, it wouldn't update the existing nodes. So the fourth option then, well, no, because that says something about doing stuff manually. So 4 options, and we're not going to use any of them. Well, unless you use this one and create some logic yourself, right? The point here isn't that etcd is bad, because it works. We rarely have any problems with it, but it goes to show that you shouldn't be trusting production documentation if you want something that's production ready. In a lot of cases, and etcd is not an exception here, documentation is aimed at getting up and running now, instant gratification. So how did we end up bootstrapping our reference platform? Well, the first thing we did was create an internal autoscaling group for the etcd cluster. We have no intention of scaling, but we're simply going to use it to determine if, well, there is a cluster to use. So it looks basically something like this. And then on every CoreOS instance, we run an etcd bootstrap service, which is basically a shell script that uses the local AWS metadata endpoint to read information from an autoscaling group. And in this case, it will read the IP addresses from healthy backends or healthy servers in this autoscaling group. It will then use these IP addresses to check if there's actually an etcd cluster running at these IP addresses. Oh, if there is etcd running, it will configure the node to join the existing cluster and write a peers file. And if no cluster exists, it will simply start a new one. This way, regardless of whether we have a cluster or not, or a semi-failed cluster, etcd will always start in the correct way. So, pulling it all together, we have infrastructure as code, we have a static host OS, or a minimal host OS if you like. We externalize data, we have high availability by default, we use auto-scaling, and finally we fix our bootstrapping issues for pretty much everything, and hopefully less of anything in the future, as well, Nomad will do 0 configuration bootstrapping in the future, which is nice. If you build your container platform according to these principles, you can create a platform where every component can be hot swapped at any time. So when we built our reference stack at one of our clients, we wondered how we should demo it. I mean, this is pretty cool. We can do maintenance at any time. We won't get paged at 3 a.m. because one instance failed. How do we demo this? I mean, you're in a development department of a large company. There are a lot of cool teams creating really visual stuff. Their demos are popular. And you're the infrastructure team. Your demos are invisible. So we were like, how are we going to do this? But it gave us an idea. If all these demos of the development teams are so popular, what if we hot swap the entire platform during the demo? Because we have like 10 teams using the platform with 100 people watching. What if we hot swap the entire platform while they're using it and see what happens? We did. We simply terminated every node one by one, each time waiting for the replacement node to become healthy, then move on to the next. And the first time we did it, we did this by hand, just to see if it worked. But you can basically automate this. You have your health checks, you have things like AWS CLI, pick your favorite scripting language, and well, kill a node, check the health check. If it becomes healthy, kill the next one. But the question is, did it work? Did we get 10 angry teams? Well, basically, it worked. Nobody noticed. So now you know what you need to do to create a hot-swappable container platform. I want to thank you for your attention and enjoy the rest of the conference.